Today, this couple is transforming an abandoned scrapyard into a functional homestead where a container house serves not only daily living but also the local community around their workshop. Every reused material here has a purpose, and every construction choice is based on hands-on experience, not theory. Welcome back to Quantum X. If you care about real-world building, off-grid living, and practical design decisions, stay with us until the end, because every small detail in this build matters. The chosen site is an old warehouse set close to natural scenery and near a river. For a small house or container build, this offers clear microclimate advantages, but it also requires early control of foundation stability and moisture management. The work begins with selective demolition. Instead of clearing everything, the team salvages intact bricks and concrete blocks to reuse them as a new foundation. This approach reduces cost, limits construction waste, and aligns with sustainable homestead principles. From a technical standpoint, reused foundation materials must be sorted, structurally assessed, and reconfigured to match the load patterns of a container structure. Reuse here is deliberate engineering, not improvisation. After demolition, the soil is cleared of gravel, stones, and large concrete fragments. This step is critical to prevent localized settlement, a common failure when old ground is reused without proper preparation. The site is then leveled manually, not just to create a flat surface, but to control elevation, especially important on land close to a river. The soil is leveled without overcompaction, allowing natural drainage to remain effective. Once the ground is stable, the team marks the exact foundation points. For container houses, these points must align with the load-bearing corners and edge beams. Even small errors can introduce frame torsion. The stage concludes with excavating the foundations to the required depth, ensuring frost protection and long-term structural stability. Once the site is fully cleared and the foundation pits are completed, the team proceeds to pour the concrete footing pads. For container structures, continuous foundations are unnecessary, but the footings must be precisely positioned at load-bearing points and reach sufficient compressive strength. At the same time, the drainage system is installed. On land close to a river, drainage is not only about flood prevention, but about reducing long-term moisture pressure on the foundation, a critical factor for the durability of the steel structure above. Technically, combining foundation work with drainage installation minimizes rework and ensures that surface water and groundwater are directed away from the foundation zone from the very beginning. Bricks salvaged from the old warehouse are not discarded. They are reused to increase the density around the foundation footings, filling voids around the newly poured concrete. For over 25 years, it served as a place to stockpile building materials and valuable items, a direct reflection of the region's history. Until 1989, Czech Republic remained under a communist system. With limited access to resources, people learned to preserve anything that could be reused: bricks, steel, and construction components. The two containers are fully cleaned. This step allows a proper structural assessment of the steel frame before the containers are repurposed as long-term living spaces. The team applies a hot-torched bitumen waterproofing membrane to the foundation footings. This layer plays a critical role in preventing ground moisture and capillary water from reaching the concrete and steel structure above. A crane is then used to lift and position both containers onto the prepared foundations. Placement accuracy is critical, not only in location, but also in leveling and frame alignment, since containers are not designed to tolerate torsional loads. The containers are arranged in an L-shaped configuration, a common solution in tiny house design. This layout separates functional zones, opens the structure toward the landscape, and creates a technical core that supports ventilation and future expansion. The overall layout is organized in an L-shaped configuration centered around a covered patio. This approach works particularly well for container housing as it preserves the linear nature of containers while creating a semi-enclosed living core. The left container functions as the primary public zone, with the entrance positioned off-axis to reduce direct cold air infiltration. The kitchen is placed adjacent to a large portal window, allowing deep natural light penetration and a strong visual connection to the patio. The right container acts as a buffer zone. Its narrow, horizontal windows provide daylight and cross-ventilation while minimizing heat loss, a practical response to Eastern European climate conditions. The covered patio serves not only as an outdoor living space, but also as a thermal transition zone, reducing temperature shock between interior and exterior. Overall, this layout demonstrates a balanced integration of function, climate strategy, and container-based structure. The left container undergoes complete removal of its original walls and flooring. This unit is subject to the most structural modification, as it will host the large portal opening and expanded living space. Stripping the interior allows direct access to the load-bearing frame, enabling reinforcement before any major cutouts are made. The second container remains largely intact structurally. Work here focuses on odor treatment and interior cleaning, a critical step when repurposing used containers. Residual odors often originate from industrial cargo and aged coatings, and if left untreated, they compromise indoor air quality. Technically, this approach establishes clear functional roles between the two containers, one serving as the primary living volume, the other as a buffer space, reducing structural risk and optimizing the amount of reinforcement required. After the left container is stripped of its original walls and flooring, a new concrete slab is poured directly in place. This slab provides a stable surface while adding thermal mass, helping reduce temperature fluctuation during cold seasons. Behind the second container, the ground near the riverbank is regraded and leveled. The intention here is not to build outward, but to open up views and airflow, fully leveraging the natural landscape and the cooling microclimate created by the water. The stage concludes with the installation of a wooden I-beam joist roof system, forming a continuous flat roof over both containers and the entire patio. This roof unifies the structure, offering weather protection while stabilizing light, heat, and moisture conditions below. At this stage, the project enters a phase that defines long-term performance. The main structure is now stable, and the next focus shifts to finishing the roof, walls, and flooring, the layers that directly control heat retention, moisture protection, and year-round livability. Once the I-beam joists are fully installed and leveled, a first layer of wooden sheathing is laid, forming the structural base of the roof system. This layer distributes loads and establishes a flat working surface. A first waterproofing and insulation layer follows, installed continuously while leaving openings for roof skylights. Defining these openings early avoids later cuts and preserves the integrity of the protective layers. A second layer of wood sheathing is then added, increasing roof stiffness and creating a technical cavity for insulation. Above it, a second waterproofing and insulation membrane is applied, serving as the final barrier against rain, snow, and thermal stress. The process concludes with the installation of glass panels into the roof openings, allowing natural light deep into the interior without compromising the building envelope. The roof glazing system above the patio is not placed randomly. Structurally, each glass opening is positioned between I-beam joists, allowing roof loads to bypass the glazing rather than bearing directly on it. Each opening is built as an independent box frame, rigidly tied into the surrounding timber structure. This ensures the glass serves only as a daylight element, not a load-bearing component, a critical measure to prevent cracking caused by thermal movement. From a microclimate perspective, placing skylights above the patio introduces top-down natural light into a semi-outdoor living zone while maintaining full weather protection. Overhead light reduces glare and avoids localized heat gain typical of west-facing vertical glazing. A key detail is the slightly raised skylight curb above the roof plane. This promotes rapid drainage of rain and melting snow, minimizing water pooling, one of the primary causes of waterproofing failure around roof glazing. All timber used in the project is reclaimed wood, sourced from old stockpiles and recut at the former barn's sawmill. Processing the wood on site allows precise sizing, removal of damaged sections, and reduces reliance on new materials. As wall construction begins, the team first erects the wall framing, clearly defining load paths, openings, and service cavities. The timber frame acts as an intermediate layer, separating the container's steel structure from the exterior cladding. Once the frame is in place, wooden boards are installed as wall sheathing, forming the new building envelope. This method leaves room for insulation, service routing, and future maintenance, aligning with the project's flexible and long-term approach. The entire partition wall between the two containers is removed to merge them into one large, continuous space. This is the most invasive structural intervention, as container sidewalls normally contribute to shear resistance and overall frame stability. The wall system is carefully insulated, starting from the interior. Mineral wool insulation is placed tightly within the wall framing, stabilizing indoor temperatures and reducing heat transfer from the container's steel structure. Next, spray-applied insulation is applied directly onto the timber surfaces. This method is fast, seals small gaps effectively, and is particularly efficient at eliminating thermal bridges, a common issue in container buildings. As a result, construction progress accelerates noticeably. On the exterior, rigid foam insulation boards are mechanically fixed across the entire wall surface, followed by a full plaster render. This outer layer protects the insulation, forms a continuous building envelope, and ensures resistance against wind, moisture, and cold climates. If you enjoy this documentary-style rebuild with a focus on real construction decisions, materials, and practical thinking, please like, share, and subscribe to the channel for more projects like this. And if you have your own insights or experience with container homes and off-grid living, feel free to leave a comment below. Those conversations help grow a more grounded and informed community. In the final stage, the team levels the yard surface and installs interlocking concrete paving blocks. Technically, interlocking pavers offer high load-bearing capacity and effective drainage thanks to the small joints between each block. Once the wall system is fully completed and stabilized, the team proceeds with installing steel-framed glass doors and windows. Steel frames allow for large openings while maintaining structural rigidity and geometric accuracy, which is especially important in container-based buildings where steel structures expand and contract with temperature changes. The placement of each opening is carefully considered, not only for daylight, but also to frame views and enable natural ventilation. Deep daylight penetration reduces reliance on artificial lighting, while opposing openings support cross-ventilation, a passive strategy with long-term benefits. Before applying the reflective aluminum membrane, the entire electrical wiring system is pre-installed and left in place. This step prevents the need to cut or breach the building envelope after completion, preserving insulation and moisture control layers. Technically, pre-routing electrical lines allows wiring to remain within a dry service cavity, separated from the container's steel structure, reducing risks of condensation and corrosion. All connection points are pre-defined based on functional layout, minimizing future modifications. With all openings secured, the exterior walls are then wrapped in a reflective aluminum membrane. This layer acts as a radiant heat barrier, reflecting a significant portion of solar radiation before it reaches the multi-layer wall assembly beneath. From a technical perspective, reflective membranes are only effective when properly positioned within the wall system, combined with air gaps and insulation layers. When done correctly, the building retains heat during winter while limiting overheating in summer, a critical balance for flat-roofed structures with large glazed areas. The result is a highly controlled building envelope, where each layer serves a specific purpose, working together to deliver thermal stability, durability, and long-term livability. Once the exterior envelope is fully controlled for heat and moisture, work shifts to interior finishes. Gypsum boards are installed on the walls, creating smooth surfaces that are easy to finish, while also helping regulate indoor humidity. Technically, gypsum is a lightweight finishing layer that allows for future modification and maintenance, well suited to projects developed in stages, such as this homestead. In the left container, where most of the original steel structure has been removed, the team finishes the interior using a gypsum wall system. This solution works well with the new framing, remains lightweight, and allows effective integration of electrical services, insulation, and surface finishes. In contrast, the second container retains much of its original steel shell. In this case, a full gypsum wall system is unnecessary. Instead, rigid insulation foam is applied directly to the surface, followed by steel mesh reinforcement and plaster rendering. Technically, this approach takes advantage of the container's inherent rigidity, reduces additional material weight, and creates a solid, impact-resistant finish. Two different wall systems, each chosen to suit the structural condition of its container, both optimized for performance and efficiency. The next step is installing wood-look ceramic floor tiles. This material delivers the warmth and visual character of wood, but with superior durability, moisture resistance, and low maintenance, ideal for concrete slabs and environments close to a river. Combined with the thermal mass of the concrete slab below, the tiled floor contributes to more stable indoor temperatures and long-term performance. During finishing, tile leveling spacers are used to ensure a uniform floor height, compensating for minor irregularities in the base. It's a small detail, but one that directly affects durability and long-term comfort. Once the tiles are set, grout is applied to lock the surface together, increasing load distribution and preventing moisture from penetrating into the sublayers. At the same time, the gypsum walls in the kitchen area are painted. Beyond appearance, the paint seals the surface, reducing moisture absorption and dust accumulation in a working kitchen environment. These steps mark the transition from structural construction to a livable interior. The kitchen area is fully finished with tile flooring. As a space exposed to moisture, heat, and frequent cleaning, durable and water-resistant materials make long-term technical sense. In the living and sleeping areas, however, a shortage of tiles leads the team to install OSB boards as a temporary floor. The OSB provides a flat, structurally sound surface suitable for daily use. A temporary carpet is then laid on top to improve comfort and thermal feel. Technically, this is a flexible solution. The OSB functions both as a short-term finished floor and as a future subfloor when final materials become available. This approach reflects the project's core philosophy, building in phases, prioritizing essential functionality first, and upgrading gradually as resources allow. In both the sleeping area and the main living space, wall panels are selectively installed, focused on the bed wall and the TV wall. This is not purely aesthetic. Technically, panels provide a flat, rigid, load-bearing surface, allowing equipment, shelving, or headboards to be mounted without additional hidden reinforcement. At the TV wall, panels help reduce vibration and sound reflection, improving audio-visual comfort in a container structure where metal surfaces tend to amplify echo. Around the bed, the panels create a more enclosed feel while protecting the insulation layer from daily wear. The layout reflects a clear construction logic: reinforce where impact and load occur while keeping the rest of the interior light, adaptable, and easy to modify in the future. This project is not about a perfect house, but about adapting, reusing, and building with what is available, turning scrap materials and old containers into a real living space by the river. If this kind of story resonates with you, leave a comment and share your own perspective or experience. Like, share, and subscribe to Quantum X to follow more real-world build stories like this. Thank you for watching until the end. See you in the next episode.